Hi everyone, welcome to part 2 of the video lecture on the topic of modern portfolio theory. Modern portfolio theory, or sometimes we refer to it as mean variance model for portfolio selection, or Markowitz mean variance optimization model, is the building block for management of portfolios. This theory helps us identify the goal of portfolio selection as a construction of portfolios that maximize the expected returns, and at the same time keeping the levels of risk for that portfolio at a level that the individual investors are okay with. So keeping the risk preferences of the individual investors in mind, the portfolio is constructed in a way so that the goal is to maximize the expected returns that are achieved from the overall portfolio. In the previous video, part 1 of modern portfolio theory, we discussed some basic concepts around the underlying assumptions for modern portfolio theory, and we also introduced a few formulas that help us calculate the return of a portfolio as well as the expected return of the portfolio. Just to revise, the difference between an observed return and expected return is the observed return has already been observed, so we know exactly for sure what the value would be, whereas expected return is a forecast for the future returns of the portfolio. We're going to continue with the same discussion for this video as well, and we'll introduce some other new concepts that help us formulate and understand modern portfolio theory. So we're going to start off this video with slide number 7 of the slide deck and then continue from there. So far, we know how to measure the return of a portfolio as well as the return of an individual risky asset, but we're going to extend that discussion and learn how we can measure the risk of a portfolio and the risk of the individual stocks that will, or individual assets that will be a part of that portfolio. Investors have used a variety of definitions to describe risk over the years, but the most commonly used definition of risk is by using variance and standard deviation as a proxy for risk. And this concept was identified by Markowitz. He quantified the concept of risk using standard deviation and variance. Now, as we all know, variance is defined as the square of the value of standard deviations. Because computations are easier in terms of variance than they are in terms of standard deviation, so in a lot of the formulas for modern portfolio theory, we're going to be using variance more often than we use standard deviation, but we all know that both of them measure the same thing. They both measure the dispersion or the spread of the values around the average or the mean of that particular risky asset. So in the reference of portfolio theory, variance is a measure of the dispersion of possible rates of return outcomes around the expected return. So whatever the expected return is, how far away from the expected return each of the individual possible returns are is what the variance measures. And equation 5 here on the slide helps us calculate the variance for a risky asset, which we're calling Ri. I is the subscript that helps us identify the individual asset or the individual stock that we are calculating the variance for. And if you recall from the example for calculating expected returns that was demonstrated in the video, part 1 video of the same lecture, we assumed a certain probability distribution for our risky asset because we're not exactly sure what the future value of the return of that asset will be. So assuming a probability distribution, we get the values of P1, P2, P3, all the way till Pn using that probability distribution. So these numbers would come from the probability distribution that is assumed or is imposed for that individual stock I or asset I. And because variance measures the dispersion around the expected value or the mean, you'll see that even in the value in the formula that helps us calculate variance, we're using the probability multiplied by the difference between the individual return value from the expected value squared up. And we do that for each possible return value. Take its difference from the expected returns and then square it up and multiply it with the respective probabilities for that return value. So we're going to demonstrate an example just to learn how to use this formula correctly. But just remember that once we have calculated the variance, it's very easy to go to the standard deviation and calculate standard deviation, which will simply be a square root of the variance that was calculated using equation 5 here. How we're going to use equation 5 in Excel to help us get the variance of stock XYZ. I'm going to use the same numbers that we used for calculating the expected return of XYZ in part 1 of this video. So we assumed that the asset under consideration is stock XYZ, which is a risky asset, so we're uncertain of what the rate of return for XYZ is going to be in the future. Assuming this given probability distribution on the rate of return for stock XYZ, we are considering that the return for XYZ can take any one of these 5 values, and the probability that it takes any of these is given in column C over here. So using these rates of returns and the probability of occurrence, we came up with the expected return for XYZ as the sum product of these potential rates of returns with their respective probabilities. One thing that you should keep in mind is that for any probability distribution that you're assuming for a random variable, the sum of all the probabilities has to come up to 1. Otherwise, it's not a valid probability distribution. And in this case, we confirm that by calculating the sum of all these probabilities, and it does indeed come out to be 1. And remember that these numbers here in column B are considered to be in percentages. So the rate of return for stock XYZ can take a value of 12%, 10%, 8%, 4%, or negative 4%. So the expected return or the mean of XYZ comes out to be 7%. Now that we have the expected return, we're going to use equation 5 that we just saw in the slideshow to help us calculate the variance for XYZ. So to do that, first recall from the formula that we were using the difference between each of these individual rates of return and the expected return for XYZ. So let's calculate that. I'm going to create a column here which helps me get the difference between R and expected value of R. So this will simply be the first rate of return minus the expected value. And since the expected value or the expected return stays the same throughout, I'm just going to put a constant cell reference here by adding $signs in front of both C and 10, so that when I drag the formula down to get the rest of the differences, this number does not change. The keyboard shortcut for this in Windows is F4. So when you drag this down, you get the difference between each of these individual returns and the calculated expected return for XYZ. The next step would be to square this number up. So that is simply going to be the square of the values that we just calculated in column D. And I'm going to drag this down all the way to help me get all the differences for the possible 5 rates of returns. Now that we have these two columns filled up, we have all the information and cell references we need to calculate the variance for X, Y, Z. So let's calculate the variance. If you recall from the formula which is given in equation 5, we have to multiply the individual probabilities with these square differences and then add them up. And the simplest way to do that in Excel is using the sum product formula, where the first set of cells would be these probabilities. Make sure that you don't add this 1 in the formula because that's not what we need in the formula. Comma. The second set of cells would be the differences between the returns and the expected returns squared up. So, sorry, oops, my cell is referenced as a percentage. I'll convert it to a general number. And now we have the variance for our stock XYZ. Remember that these rates of return were in percentages, which is why our variance is also going to be in percentages. So this is how you would use the formula that is given in equation 5 to help you calculate the variance of XYZ for a risky asset. Once you have the variance, you can also calculate the standard deviation for XYZ, and the standard deviation would simply be the square root of this variance that we just calculated. So the standard deviation for XYZ is 4.91. Moving back to our PowerPoint presentation, we just use an Excel example for stock XYZ to help us understand how we can use this variance formula to calculate the variance for a risky asset RI and also get the standard deviation. Moving on. Now that we know how we can measure the risk and return for individual risky stocks or risky assets, we are now going to move on to calculate and measure the portfolio risk of a 2-asset portfolio. Now remember that in a portfolio of assets, you can have multiple assets as a part of your portfolio. You can have 10 assets, 20 assets, and so on. But the easiest way to understand how we measure the return and risk of a portfolio is by considering an example of a 2-asset portfolio where we only have 2 assets that are a part of our portfolio. So in order to measure the variance of or the risk of the portfolio, we're going to first calculate the variance of the portfolio. The variance of a random variable is a measure of the dispersion or the variability of that random variable around its mean value. And we saw how we can calculate it for an individual asset. Now, in this case, we have 2 such individual assets as a part of our portfolio. Those 2 assets are named RI and RJ. So assuming that our portfolio RP is comprised of these 2 assets RI and RJ, in order to get the variance of the whole portfolio RP, we have to calculate the individual variances of each of these 2 stocks first. So variance RI and variance RJ would come from a calculation similar to what we just did in the example. Then we consider the weights of each of these individual assets in our portfolio. So let's say that 40% of our portfolio amount is invested in RI and 60% is invested in RJ. In that case, the weights for RI and RJ respectively would be 40% for WI and 60% for WI and 40% for WJ. So these weights over here are going to be percentages as well, or if you want to use decimals, that's okay too. You would have to square up these weights and use them in the formula to get the variance of the whole portfolio. What you'll notice is that in our calculation for variance, it's not simply a sum of individual variances, but it also has a third term where we are introducing a new term called COVRI of R and RJ. This refers to the covariance between Ri and Rj. Now, in order to understand why the portfolio includes not just the sum of the variances but also the covariance, we have to understand the mathematical properties of the variance. If an asset is riskless or it has a dispersion around the expected return of 0, then the variance of that asset becomes 0. However, if the asset has a non-zero variance, which means that it can take values other than the expected value, then you have a positive variance. And when you have positive variances in your portfolio for individual stocks, you can use this equation here, equation 6, which states that the variance of the portfolio return is the sum of the squared weighted variances as well as the covariance included in this formula over here. So we're going to deep dive into what do we mean by covariance, but just to introduce covariance, it basically helps you understand how Ri and Rj move when the other stock changes values. So if you have a positive covariance, then it means Ri and Rj change in the same direction. If Ri increases, Rj will also increase. If Rj increases, Ri also increases. If the covariance is negative, it means that they move in opposite directions from each other, which means if Rj increases, Ri will go down, and if Ri increases, Rj will go down. So let's try to understand the concept of covariance in slightly more detail. Covariance has a precise mathematical translation. Its practical meaning is the degree to which the returns of the two assets covary or change together. Covariance is not expressed in any particular unit, such as a dollar sign or percentages. Positive covariance means that the returns on the two assets tend to move together or change in the same direction, while negative covariances mean that returns tend to move in opposite directions. The covariance between any two assets, I and J, can be computed using the formula which is given in equation 7 over here. And what you'll notice is that this formula is very similar to equation 5, or the formula for variance. The only difference between these two formulas, equation 5 and equation 7, is that in equation 5 we had this value squared up, whereas in equation 7, because we're considering two different assets, it's the difference of Ri with its expected return and the difference of Rj with its expected return multiplied by the probability for that particular instance. Let's use the same example that we used for variance to help us understand how we can use this formula for covariance as well. I've switched my screen to the Excel sheet that I'm going to use to help us demonstrate equation 7. You'll remember that we had seen this part of the example earlier in the calculation for variance. We've added a new asset to the mix now. Initially, we had only one asset, which was stock XYZ. Now we have two assets, and the second one is stock ABC, which has, again, 5 possible rates of return with their respective probabilities of occurrence. So the probability distribution on ABC is given by the cells that I've highlighted right now. And just to make sure that all these probabilities equal to 1, we calculate the sum, and it does indeed equal to 1. So now we're going to use the covariance formula that was given in the slideshow equation 7 to help understand how we can apply that formula to calculate the covariance between XYZ and ABC. If you recall from the formula on the slideshow, we first had to calculate the expected returns for each of these individual stocks and then get the differences between the expected returns and these individual returns so that we can use them in the formula that was given to us. So just to recall and revise the formula for expected returns, I'm going to first calculate the expected return for XYZ. We've done this earlier as well. So it was simply a sum product of the rates of return with their respective probabilities. And that comes out to be 7% as earlier. Now we're going to calculate the expected return for ABC. And that will be a sum product again, but this would be a sum product of the rates of return for ABC along with the individual probabilities for those rates of return. And that comes out to be 10%. The expected return for XYZ comes out to be 7%. Now that we have these two individual expected returns, we are going to extend our existing table to help us fill out a column where we can store the difference between the returns and the expected return first for XYZ and then for ABC. So the difference between each individual return for XYZ would be the value of the return minus the expected return. And since the expected return stays the same throughout the calculations, I'll put a $sign in front of the cell references so that it does not change when I drag the formula down. And then you can drag this all the way down so that we get the differences for each of the 5 values that XYZ's return can take. The same way we're going to calculate the difference between the returns for ABC from its expected value. And again, I'll put constant cell references. Remember that the keyboard shortcut for this is F4. Once you have your cursor in there, you can press F4 and automatically get these $signs added there. And when you drag it down, it's going to give you the differences for ABC from its expected returns. So now that we have these two columns calculated, we can create a column where we store the product of the differences that we just calculated. So that would be 5 multiplied by 11. And you can simply drag this down all the way to get all the products of the differences. Now we have everything we need to help us calculate the covariance between XYZ and ABC. Which is equal to the sum product of the probabilities. Notice that the probabilities for both XYZ and ABC are the same. So, and this is usually be the case. So you can pick and choose any of these columns, E or C, to use in the formula here. It doesn't matter. And this will be a sum product of the product of differences that we just calculated. And that's going to give you the covariance value as 33.96. Now that we know how we can calculate covariance, let's try to understand the relationship between covariance and correlation. The term correlation we're familiar with because we've used this in other topics that we've covered throughout the course as well. Especially in regression, we use the correlation coefficient and the R-squared values a lot of the times because it helps us understand the magnitude of relationship between two variables X and Y. So in this case, we're going to learn how covariance and correlation are related to each other. The correlation is related to the covariance between the expected returns for the two assets. So specifically, the correlation between the returns for, let's say, asset I and J is defined as the covariance of the two assets divided by their individual standard deviations. Dividing the covariance between the returns of the two assets by the product of their standard deviation gives us the correlation between the two assets. Because correlation is a standardized number, the fact that we divided it by its individual, the covariance by its individual standard deviations, it's a standardized number, which is why correlation is comparable across different assets. So, for example, if I have two assets which are measured in US dollars, the returns are measured in US dollars, and a third asset which with returns measured in Canadian dollars, I cannot compare the covariance of two of these assets with the third asset in consideration because their units are different. But I can compare the correlation of the assets in dollars with the assets in Canadian dollars because correlation is comparable across assets and it does not depend on the units of measurement. One thing that we can also recall from regression and the concepts around linear regression are that the correlation coefficient value ranges all the way from +1 to -1, where +1 means that there's a perfect positive relationship between the two variables, which also translates into perfect co-movement. So they both basically move in the same direction perfectly, whereas -1 denotes perfect co-movement in the opposite directions. So if Ri goes up, Rj will go down. Also note that because standard deviations are always positive, they're squared values, so you never get a negative standard deviation number. The only way correlation is going to be negative if a covariance of the two assets is negative. So that way you can understand the relationship between the two is, oops, this looks like an error here. This should be correlation. Sorry about that. So continuing my thoughts there, correlation, it simply helps you understand covariance, but in a more standardized manner because you're dividing it by the standard deviations. So a correlation of 0 implies that the returns are uncorrelated, which means that you don't see the covariance of Ri and Rj being a positive number, which is why correlation is also 0. So when covariance is 0, correlation is automatically 0 as well. So far, in order to understand portfolio theory, we have gone over the formulas to calculate returns for both individual stocks as well as portfolio of multiple individual stocks, as well as measuring risk and covariance for individual stocks and the portfolio of individual stocks. So if we're trying to measure the risk of portfolio consisting more than two assets, all the examples that we've covered so far have only had two assets in there. But if we keep adding assets in there to increase the number of assets in our portfolio, the way the variance formula changes is you still have the individual variances of all the assets involved, plus you have the covariance terms added for each additional stock that is included in your portfolio. So basically, in other words, when you add a third asset to your portfolio of two assets, then you also need to consider the covariance of that third asset with the previous two assets in your portfolio that were already there. So this variance formula keeps expanding more and more and keeps including additional covariance terms which are pairwise, so you have to add all the possible combinations of covariances depending on how many assets are a part of your portfolio. We're not going to expand this formula further, but this is just for your reference so that you can remember that when you keep adding additional assets to your portfolio, you have to consider the covariance of that additional asset with all the existing assets that are a part of your existing portfolio. Now let's try to understand what we mean when we say portfolio diversification is a good thing and all investors should aim for portfolio diversification. We always hear in finance that investors are talking about diversifying their portfolio. It basically means that an investor is trying to construct a portfolio in such a way that the overall portfolio risk is reduced without sacrificing the return. That's a very general statement to make, and it's true, but in practice, how do you achieve that diversification? And if you do achieve diversification by including multiple stocks in your portfolio, what should the optimal allocations of those stocks should be? And those are the questions that modern portfolio theory helps us answer in a very precise mathematical manner. So for example, an investor might argue that a portfolio should be diversified by investing in stocks, bonds, and real estate. While that's a reasonable assumption to make, the first question that you should ask is how much should be invested in each asset class? That is, if I have $1 million to invest, how much of those million should be invested in stocks, how much should be invested in bonds, and how much should be invested in real estate so that the allocation is appropriate in a way that it is giving us the maximum return with the minimum risk. Some investors might look at diversification as not multiple asset classes, but just one single asset class, but multiple versions of that asset class. So for example, if an investor is building a portfolio of stocks, all the assets in the portfolio are in the same asset class. They're all stocks, but which companies should be added to the portfolio so that the goal of diversification is achieved? All of these questions were unanswered before Markowitz's diversification strategy was introduced, because everybody in finance identified the need for this diversification, but there was no clear strategy to do that. And Markowitz's diversification helped us understand that strategy as a formulation of the asset's risks in terms of the overall portfolio rather than in isolation. So for example, if I have an asset stock XYZ, the risk of that asset is the variance of the asset. But when I add it to my portfolio, the risk of my portfolio is going to depend on not only my existing portfolio's variance and the variance of the newly added stock XYZ, but also how XYZ is covariated with my existing stocks in my portfolio. So that's the major contribution of Markowitz's diversification strategy. It's primarily concerned with the degree of covariance between asset returns in the portfolio. So what Markowitz's diversification seeks to do is that it combines assets in a portfolio with returns that are less than perfectly positively correlated. So if you look at the variance formula, which is a measure for our portfolio risk, moving all the way back to this previous slide where we introduced variance as a measure of risk for the first time, what you'll see is that if the variance of our P is high, that means that the variance of our I is high, the variance of our J is high, as well as this covariance term is also high. However, if we select I and J in such a way that this covariance is negative, what this does is, although individual variances of our I and our J could be high, but because of the negative covariance between our I and our J, our overall portfolio risk actually decreases by adding this additional asset to our portfolio. So that's the whole basic underlying concept of modern portfolio theory, is identifying covariances that are negative, which will help us reduce the overall risk of our portfolio. Now that we know how covariance and correlation are connected to each other, let's use our previous example to help us calculate the correlation between the two stocks that we are already familiar with, XYZ and ABC. We already have the covariance value for our stocks, and we're going to use the formula that was given in equation 7. I think, it was equation 8. We're going to help us get the correlation value for both XYZ and ABC, the correlation between XYZ and ABC. So from equation 8, we saw that the correlation is equal to the covariance divided by the individual standard deviations. In order to get the correlation between XYZ and ABC, we need the standard deviations for both XYZ and ABC. So we already calculated the variance for XYZ in the previous example that we did, but I'll just repeat the steps here so that we can revise and recall it and help us understand how correlation can be calculated. So the variance for XYZ would simply be a sum product of the probabilities with the square root of the differences between the rates of returns and their expected values. So in order to do that, I'll select that cell reference and square it up. This way we got the same number for variance as we got in the previous example. The only reason why the method was different is I just used a shortcut. Instead of creating a new column altogether, I used the existing differences column and squared it up within the function itself. So let's calculate the variance for ABC in the same way. And that is going to be a sum product of the probabilities for ABC with the difference of ABC from its standard deviation. It's going to be the sum product of the probabilities along with the differences between the returns and the expected return. And for that, we have to square it up first, because here we are calculating variances, not covariance. And that gives us the variance for stock ABC. Now that we have the two variances, we can get the standard deviations as well for both XYZ and ABC. Oops. Which will just be the square root of these variances that we just calculated. ABC. Once we have the standard deviations for both XYZ and ABC, we can use the covariance and these standard deviations to help us get the correlation between XYZ and ABC. And that's going to be the covariance divided by the product of these individual standard deviations. and that gives you a correlation value of 0.944, which is very close to 1, which means that XYZ and ABC are positively correlated, and the correlation is pretty strong. Now that we know how to calculate both correlation and covariance, let's try to understand the effect of correlation of asset returns on the overall risk of the portfolio. So how would the risk change for our two asset portfolio with different correlations between the returns of the component stocks? That's what we're trying to understand in this part of the topic. So generally, the effect of Markowitz diversification states that as the correlation or the covariance between the returns of the assets are combined in a portfolio decreases, so does the variance of the overall portfolio decrease as well. The good news is that the investors can maintain expected portfolio returns but have lower portfolio risk by combining assets that are have small or negative correlations with each other. The bad news is that there are very few assets that have small or negative correlations. The problem then becomes of searching amongst the large number of assets that are available in an effort to discover a portfolio which has the minimum risk. So now that we understand the underlying concepts of it, this is going to help us understand how we can form a portfolio which has the maximum returns and the minimum risks for those returns. This sets the stage for a discussion of efficient portfolios and how to construct them. So we're going to stop here for the purpose of this video, but in the next video lecture, we're going to talk more about efficient portfolios and how we can construct these efficient portfolios. What your key takeaway from this video should be that when your assets in your portfolio have small or negative correlations with each other, your overall portfolio risk tends to decrease, whereas the return might remain the same or even increase. And that's the main takeaway from Markowitz diversification strategy that comes as a part of modern portfolio theory.